Welcome to the 2021 David M. Lee Historical Lecture in Physics. These lectures are sponsored by the Marvin and Annette Lee Fund, created in 2000 for the purpose of supporting a series of historical lectures at Harvard by distinguished outside speakers on topics of interest to the physics community, including undergraduates and the general audience. These annual lectures are known as the David M. Lee Historical Lectures in Physics. Professor Lee wasn't able to attend today's lecture because he's teaching this semester, but his son Jim is here, and we're very happy he could join us. Hi, Jim. So it's a great pleasure and an honor for me to introduce this year's Lee Historical Lecturer, Helen Quinn, Professor Emerita of Particle Physics and Astrophysics at the Stanford Linear Accelerator Center, Stanford University. Professor Quinn received her PhD in physics from Stanford in 1967 and was at Harvard from 1971 to 1976, when she returned to Stanford and SLAC, where she spent the rest of her career until her retirement in 2010. During her career, Professor Quinn made a number of important contributions to physics, which were recognized by a commensurate number of international awards and honorary degrees. If I tried to list her important contributions and awards, it would take too much of her lecture time, so I will mention but very few examples. Professor Quinn, together with Roberto Peccei, proposed a theory to solve the strong CP problem, which is still the most famous solution to this problem, known as the Peccei-Quinn theory. She also worked with Howard Georgi, Steven Weinberg, and others on fundamental particles and their interactions. As for awards, she has been awarded the J.J. Sakurai Prize of the American Physical Society, the Carl Taylor Compton Medal of the American Institute of Physics, the Benjamin Franklin Medal, the Dirac Medal of the ICTP in Trieste, Italy, and many others. Since retirement, she has chiefly worked on improvements to K-12 pre-college science education. She served also as president of the American Physical Society in 2004 and is a member of the National Academy of Sciences and the American Philosophical Association. So it's with great pleasure that I welcome her to Harvard to present the 2021 Lee Historical Lecture. Professor Quinn.
Okay. We turn that mic off, and this one is working. Thank you. And thank you for being here this evening. I'm going to do two things, or three things. I'm going to talk about how theories change in science with the example of the Standard Model as the one I'm talking about in detail, and the time in the 70s when that theory was what I call emerging. And I'm going to talk about my own experience as a young faculty member here at Harvard in the 70s, which was important because I almost dropped out of physics before I came back to Harvard in a free office, and the Standard Model took off and I took off with it. So let me start by dedicating this lecture to Steven Weinberg, because he's critical to my story and was of course part of this department for quite a few years, and as I say here, is a scholar at every level. I'm going to tell one short anecdote here and maybe some more at the end if there's time. So Steve and I were walking across Harvard Yard, going to the faculty club for lunch, and somehow I happened to start talking about how my young children made mistakes in English, which I considered common American errors. And should I or shouldn't I correct them? And Steve got a little bit huffy, and he said, "What do you mean, common American errors?" And I said, "The failure to distinguish between like and as if." And Steve thought for a moment. He said, "I guess in that respect, I'm as if most Americans," thereby proving himself totally unique. Also showing me that I hadn't formulated the problem right. But I think this man just had a mind that went to the root of things. No matter what he was thinking about, he thought deeply, and we all benefited from that. So for the non-experts in the room, this lecture is going to have some technical details, but it doesn't matter. You can follow the story even if you don't follow the technical details, because it's a story about physics and how it changes, or science and how it changes. Also, I was lucky. This was the golden age of particle physics. To be here at that time was to be in the right place at the right time. And that will become obvious as the theory emerges. When it's a new theory, there's lots of easy things to do to answer questions to understand this new theory. So everybody gets to contribute, and the young people are as knowledgeable as anybody else. I mean, maybe we're not as knowledgeable about some of the things that they can bring to the table about field theory, but about this specific field theory, we're the first ones doing it. And so it's really fun, and it's a wonderful time to be in physics, and we were very lucky to be here at that time. And I will tell you who we was as we go along. Of course, Howard, who's sitting right there, is one of us. I think there are 3 stages to the development of any scientific theory, and I use the biological example to make this argument here for those who are not physicists. There's a stage before the theory emerges, but lots is going on, some of which turns out to be the seeds of the new theory. So it's not obvious which pieces are going to go that way. And so there's lots going on that has nothing to do with the theory that's coming out. But there are pieces that later come together to make the theory. Then there's a stage when they come together and the theory emerges. And then there's a stage of consolidation where it's being tested and refined and maybe corrected a little until it becomes a really well-established theory with lots of evidence behind it. And that's the cycle we're talking about. And the period for the Standard Model, I say the period of emergence, you can date the beginning either in '64 when quarks were first suggested, or in '67 when Weinberg wrote his paper, A Theory of Leptons. I choose the '67. That's convenient for me for other reasons in this story. So we'll go, say, from 1967, and I put the end in 1974 when John Iliopoulos at a conference in London told the story that pretty much as we tell it today, this is the way the Standard Model should be. This is the theory that works for particle physics. All the pieces were there by that time. Of course, they weren't all widely accepted, and if you look at the report of that conference, you'll see a lot of other things happening too. And from 1974 onwards is the period of consolidation for the Standard Model. So, Standard Model of particles and interactions, the prehistory. What I mean by prehistory, I just told you, so I won't really repeat what's on this slide, except for the non-physicists, the genetics parallel is there. What's going on that builds to a modern theory of DNA and genes prior to 1905, which is the first time anybody used the word genetics. That's the prehistory stage. Okay, particles and interactions. What particles? Between 1950 and 1967, lots of particles were discovered in lots of experiments, which originally started as attempts to understand nuclear interactions, the strong interactions between nucleons, and to understand the structure of protons and neutrons, thought of as a diffuse structure of charge. And the discoveries were completely unexpected, and physics was about cataloging those discoveries and organizing them and understanding them. And here's a list of names. Particles were grouped together in groups of roughly similar mass and the same spin. And we had a whole biology of particles, zoology of particles, if you like. What interactions? Well, we knew about electromagnetic interactions, and in fact, we had a good field theory of electromagnetic interactions. It had some problems at high energy or high field value, but worked pretty well for lots of things. We had a theory of weak interactions, which we knew was sick, but because the weak interaction is weak, the leading order calculation gave pretty good answers, except all the corrections were infinite. So, or you needed an infinite number of parameters to deal with them. So that clearly was not a good theory. It was non-renormalizable in the technical terms. So we knew it needed fixing, but we didn't have a fix for it. And as far as strong interactions were concerned, we had really no theory at all. We had a phenomenological potential model of the interaction between protons and neutrons in nuclei. So that's the interactions we're talking about. The key pieces that came out in this prehistory that led to it is, first of all, the idea that there are quarks inside protons and neutrons, suggested by Gell-Mann and Zweig in 1964. But they were just a way of explaining the patterns that we'd found. There was no dynamics in the theory. There was no interactions between the quarks. Protons were made of 3 quarks. Mesons were made of a quark and an antiquark. That could fix everything if we had 3 types of quarks, up, down, and strange. And it was very attractive and at the same time very puzzling, because the quarks had to have fractional charges of the charge of a proton or a neutron, and nobody had ever seen such charges. The idea that such charges could be confined, which we'll talk about later, was not around. And so most people kind of kept the quarks in their back pocket, and until much later. So this is a piece of prehistory. So I graduated from Stanford in 1967, which I'm taking as the transition rate. What did I learn in graduate school? First of all, a little context. The percentage of women in physics at that time was 2%. PhDs, I mean, of those graduating with PhDs in the US, these are the blue curve is total and the red curve is women, from 1972 till now, or nearly now. And you'll see slow but steady increase. So you can extrapolate back to 1967 and you realize there were very few. What I learned? Well, things like the bootstrap theory, which said a proton is a composite of a neutron and a pion, and a neutron is a composite of a proton and a pion. And what that answered, I don't know. But, so I call it not even wrong in the language of Feynman. It's not predictive enough to say it's wrong. Theories that are still correct and have their application, but didn't really feed into the standard model very much. And then keeping track of this bookkeeping of particles. Those are most of what I learned. And the last piece was current algebra. Now, current algebra was really quark theory without the quarks, because we would say, let us assume that there is this algebra of currents, weak and electromagnetic currents. Well, you could derive the algebra if you assumed the quarks and you assumed that the quarks were free at high energy. So the algebra was really derived from quarks, but then we threw the quarks away and just wrote papers based on the algebra. And one of those papers was Bjorkain's paper, which leads to the idea we call Bjorkain scaling, which is how to understand basically how to plot the data for experiments where you're scattering an electron off a proton or a neutron, and the electron is transferring a lot of energy and momentum to the proton or the neutron, and you're looking at the pattern of scattering. And if the process is as this diagram is here, where there's some things inside the proton, and the electron scatters and it transfers some energy to one of the things inside the proton and knocks the proton apart, you could predict the way the energy and momentum dependence. The Q is the energy and momentum transferred, and the P is the initial momentum of the proton. And you could predict that the rates of the process depended only on this particular combination of Q and P that I have up there, not on the two variables separately. And that's Bjorkane scaling, and that was the paper that Bjorkane first gave me to read. And I started working on current algebra with him on that work. In fact, this is a very funny piece of the history. When he gave me that paper, I found an error in it. It was actually a trivial error, but Bjorkane published an erratum to his paper with me as a co-author. I don't think there's any other case that I know of where an erratum to a paper has an author that wasn't an author of the paper. But that was BJ giving credit. And I always say I've been fortunate with the people I've worked with because they've given me my share of the credit. And these experiments actually are now understood to be the experiments that discovered quarks inside the proton, and it receives the Nobel Prize for that work. So now let's go from 67 on. Standard model is beginning to emerge. This is where things come together. New observations happen, important new observations that fit the new theory. And very often new technology is a key to that. I mean, just the discovery of all these particles took the new technology of accelerators. The discovery of quarks inside the proton took the new technology of SLAC, very high energy electron accelerator, etc. The technology builds on the science, and the science builds on the technology. 1967 is a key date because Weinberg wrote a little paper called The Theory of Leptons. It was a new weak interaction theory. It had all the features that weak interaction theory needed to have, but it had, as he wrote the paper, only the weak interactions of electrons and muons and neutrinos. Why? Why did he? I mean, weak interactions, we originally called them the weak nuclear force because they had to do with hadrons. A paper about weak interactions that didn't talk about hadrons, kind of strange. And it was widely ignored, partly because of that, I think, and partly because nobody knew how to do the math to calculate the one loop corrections to see whether or not this was looking like a renormalizable theory, a theory that made sense better than the previous one. So it actually only has a couple of citations between 1967 and 1970, when the next key development happened. Well, I'll talk about why no hadrons before I go to the next key development. The other piece was, if you did the obvious thing and generalized it to the three-quark theory, it gave a wrong prediction. It said that there would be strangeness-changing weak neutral interactions, meaning no change of charge of the electron scattering via Z would give large changes-changing effects much larger than existing experimental limits. So it didn't work if you did the obvious generalization. And I think Weinberg knew this, and that was one of the reasons. But he wanted to publish this beautiful picture of how the weak interactions could work, and so he gave it just for the leptons. And that picture had all the pieces that, all the pieces that he put together to build that picture had already come along, and that's why he shares the Nobel Prize with Glashow and Salam. You could have added some other people. The Higgs mechanism, which also wasn't just Higgs, but many other people, all built towards Weinberg's paper. 1970, two critical steps. Glashow, Iliopoulos, and Mariani say, well, if we have four quarks, we can put together the weak interactions of the four-quark theory in such a way that the strangest changing neutral currents are canceled. So the theory now makes the correct predictions for the standard model. So that's the key piece. And the other piece is that Tufton-Veltman showed us how to do something called dimensional regularization, a technical way of doing a calculation at one loop. The problem was you could, without the Tufton-Veltman, you couldn't deal with cutting off the infinities to be able to calculate and see whether they balance one another out. Because when you put in what was the standard way of regulating those infinities, you broke the gauge symmetry. And that didn't allow us to do it. And Tufton-Veltman gave us a way to gauge invariantly handle that problem. And so that's where we started being able to calculate with Weinberg's theory. And it happened that's also where this story of my time at Harvard comes into this. So here's particle physics at Harvard in this period. I can barely read what's on my computer screen without my glasses, but Shelley and Sydney were faculty members. Julian Schwinger had just left to go to UCLA. Actually, he was on leave at UCLA. Roy Glauber was doing nuclear physics. Arthur Jaffe, who's here, was doing fundamental field theory, basis of QC, of non-abelian theories, and so on. But this group was doing the physics that built the standard model. Tom Appelquist was his assistant professor. Joel Primek was a junior fellow. And Joel met me somewhere when I had no job and invited me to come talk about what was happening in physics. And he and Tom and I started doing that one-loop calculation of muon decay to electrons in Weinberg's theory of leptons using the Tufton-Veltman's dimensional regularization. And that's where I came in with no job to an office at Harvard. In the fall of '71, Howard and I both became postdocs here. In '72, I became an assistant professor. Alvaro arrived as a postdoc. I've got, where did Howard, as I said here, Howard was still thinking in 2 dimensions when he got here, but Shelley quickly cured him of that. So in '73, Steve Weinberg moved from MIT to Harvard, and Howard became a junior fellow, and Enrico Poggio became a postdoc. I wrote some of the papers here during that time with Enrico as well, and Steve. And then Tom left, and then Howard became an associate professor, so did I, but I left because Dan got a job in SRI in Menlo Park. So I took my Sloan Fellowship and trotted off to Stanford for 6 months, which is when I did work with Roberto Pache that was mentioned earlier. So this period, we had a rotating but very strong crew. I also mentioned here, the reds are the people who finished up with Nobel Prizes, right? And David Politzer was a graduate student with Harvard, Eric Weinberg also. Johnny Leopoulos was a visitor just before I came, and Shelley was left and worked with him when Shelley went on sabbatical. So the whole crew here was very active in the early stages of different pieces of putting this theory together and going beyond it. So this was an exciting time to be in this department. I've just already told you that we did this one-loop calculation. Actually, very soon after we published that, Lee and Saint-Justin published a series of 3 papers, the third of which referenced our paper incorrectly as being Appelquist and Quinn, not Appelquist, Primak, and Quinn, that proved that the Weinberg theory was renormalizable. So our paper was sort of a first indication that it would be renormalizable. Very soon thereafter, they had the full-on proof. Weinberg was so excited when we told him we'd done that one-loop calculation. He invited us to his house for sherry. And I think, you know, we went down to MIT to tell him about it. And that was the first time I met him. But he said, I thought that was the case, but it's wonderful that you've done this calculation, so let's go celebrate. So I think that was the beginning of my relationship with him. 1972, what were we doing? Well, not here at Harvard, but elsewhere, there's the other piece of the standard model developing, the strong interaction part. And as I said, the original quark theory had no interactions between the quarks. A theory of quark-strong interactions put together by Gell-Mann, Fritsch, and Leutwiler, QCD, is the rest of the standard model. So it's Weinberg and all the pieces that went into the Weinberg theory for the weak and electromagnetic part, and QCD for the strong interaction part. And they all fit together because they're dealing with the same quarks. Right? And this theory did two things. It totally redefined what we mean when we say strong interaction. Right? When we invented the term strong interaction, it meant the interaction between protons and neutrons. Protons and neutrons are neutral objects under the QCD theory of strong interactions. They happen to have color charge constituents, and they interact with one another when they kept close enough together that the color charge constituents of one are interacting with the color charge constituents of another. But so it's like, you know, electromagnetism is what holds atoms together, but the interaction between neutral atoms that make molecules is also electromagnetic. Because they get close enough together, they start talking to one another about their substructure. And so the same story goes again. QCD, our modern theory of the strong interactions, is the interactions of the quarks inside the protons and neutrons. And the interactions between the protons and neutrons are a residual effect of those interactions between things which are actually strong interaction neutral objects when they're far enough apart. And the other piece said, no, a proton is not three quarks. It's a fluctuating dynamical system in which quarks and gluons are interacting all the time, and gluons are making quark-antiquark pairs, and it's a very complex system inside that proton. It's not just three quarks stuck together by some magic. And both of those things are very big changes in how we think about what's going on. And then the pieces, Georgia and Glashow were already putting the pieces together and saying, oh, these pieces fit together so well, we'll make a grand unified theory where they're really all parts of the same one theory. And they're also saying, and if you want to make any one theory of this kind, you have to have full generations, meaning you have to have, for every set of leptons that you have, you need a set of quarks. So the charges cancel and you get anomaly, what technical term, anomaly cancellation. All of these pieces are emerging in parallel, right? But again, the strong interaction theory was a new kind of math, a complicated theory, and needed work to understand it. But also, in '72, I think this was very brave. Kobayashi and Moskawa, most people had not accepted four quarks. But Kobayashi and Moskawa were looking at this theory and said, well, there's another piece of physics which we know experimentally and we've never understood. And that's what's called CP violation. It's a small difference in the laws of physics for matter and antimatter. They're essentially mirror images of one another, but not quite. What is that difference? We couldn't write theories back when that was discovered in 1956, I think it was the year, right? 1964, got the years wrong. Fitch and Cronin told us experimentally that such a breaking was necessary in the theory, and nobody wrote theories that could explain that. But Kobayashi and Moskawa said, well, if you take the standard model and you add one more generation, so you need 6 types of quarks instead of just 4, you can explain that. They actually said, or if you add additional generations of Higgs. So there were 2 answers. One of those answers turns out to be, they may both be true, but at least we now know that there's the 3rd generation of quarks. There's 6 of them, not the original 3, but 6. So it was pretty bold to put that down as an extension of a theory nobody believed in, but it is indeed the answer which experiment has shown us fits beautifully. I'll show you some data later. 1973. I told you current algebra worked and we made good predictions from it. if you believed that the quarks behaved as if they were free at high energies. QCD is a theory where that is so. The interaction gets weaker as the energy gets higher. And that was also a new thing. It was a Nobel Prize new thing. For Politzer here, a graduate student, Wilczek at Princeton, a graduate student, and Gross, Wilczek's super advisor. Sidney Coleman, who was Politzer's advisor, was actually at Princeton talking to Gross and Wilczek. Gross and Wilczek were doing the calculation. David was doing it here. David came to talk to me and Tom, telling us his result. We said, well, that's really nice, but is it gauge invariant? Now, anybody who learns about this today immediately knows it's gauge invariant. But it took David a week or so to convince us. And so we delayed him publishing his result, and the two papers came out on the same day. So that's a little bit of the story there. But again, another really exciting piece of physics going on in this building at that time that was actually done by a graduate student. Okay, so now we've got all the pieces. But we don't have all the experimental evidence. So while here at Harvard, we were all totally convinced this must be the answer, it just was too pretty not to be the answer, the world was not so well convinced. And when, as I said, John Iliopoulos gave the talk in 1974 that put all these pieces together, if you look at the proceedings of that conference, you'll find it's definitely a minority view. But it didn't take much longer because there was a quick confirmation. But I would say by 73 here it was kind of taken for granted. Shelley talked, not the extra generation for CP violation, but I remember Shelley talking all the time about the 12 known quarks, by which he meant 4 flavors and 3 colors. And Shelley and Howard were talking about SU5, going beyond the standard model to the next level of understanding. Shelley was full of new ideas all the time, and Howard was good at shooting them down when they were obviously crazy, so he would call them poppycock. And Shelley usually would fight for a little while, but pretty soon took that as answer. So they got lots of things done as they worked together. So the standard model was here by 73. And there were maybe 5 other places in the world that were as convinced as us. But I think it's just amazing to be in a place where something like that is happening over a 3 to 4 year period, where things, ideas from here and from elsewhere are just building together and everything fits. And we were happy. Okay, just to show how happy we were, here's a completely crazy paper we wrote. I think it's the only physics paper published as a play, because we were having fun and playing games. And we actually performed the play right in this room. Shelley, because Howard was a co-author, Howard and I were part of the play. I was significantly pregnant with that young man standing there. And we were just having fun. We were trying to explain a rumor which actually went away about an experimental result. Shows the risk of latching on to preliminary results from experiments. And we invented this thing called fancy, which is having larger isospin representations with fundamental particles. But we were playing games with ideas based on quarks, because quarks were obviously the interesting thing to think about. Now, in the spring of 1974, just down the hallway here, I was talking to Tom Appelquist and David Politzer about the 4th quark, and how if you had the 4th quark, you would expect in electron-positron scattering to find narrow resonance states, because you made a new quark an antiquark when you got to the mass of that 4th quark. And there were some estimates as to where that mass should be, but it hadn't been seen. And so we were having this discussion, and as usual, Shelley and Howard and Alvaro came down the hall to get us to go to lunch. And Shelley listened for a while to what was being said and said, "Do you mean to say I'm in a room where all of the people believe in quarks?" Now, there were 6 people in that room, and this is spring of 1974. Charm. Believe in charm, sorry. And there are actually 7, because the baby was still was in the room too. He didn't count. By the end of 1974, you could get a much larger room, and by the end of 1975, essentially the community was convinced, because experimentally charm was discovered. Now, before we get to that discovery, the other problem. Quarks and gluons have these fractional charges. Why don't we ever see fractional charges? The answer is they're confined inside the protons and neutrons. And I think the best explanation that I can give as a non-technical explanation is so let's do the experiment. We collide an electron and positron. We make a quark and an antiquark flying apart. Between them, there's color fields, very intense color fields, with enough energy density to make more quarks and antiquark pairs. So there's many possibilities of ways that that energy density can redistribute itself into quarks and antiquarks, which arrange themselves into hadrons flying apart. And the probability of getting them far enough apart that you can observe them separately before the string between them is broken by production of additional quarks and antiquarks is very low. It's like the probability of finding all the air in this room under this table. Perfectly possible physical state, just never observed. That may or may not be the right answer, but I think it's actually a very plausible way to think about it. And makes confinement make sense in a way that actually never has been. I mean, there are lattice calculations which are actually equivalent to that argument that show confinement. And there are formal arguments which are less intuitive that begin to show it, but there's not really a complete formal proof of it. But it's an understandable phenomenon to me. And the other thing is, the argument I just gave you is easiest to see in theories like the real world, where the masses of the quarks are small compared to the masses of the protons and neutrons made of quarks. If the quarks are heavy compared to the scale that comes out of the interaction theory that defines the size of the proton and neutron, it's a little more difficult to see this argument. So my argument may not be completely general, but it certainly explains the real world in a simple way. So we had all the pieces, as I said. John Iliopoulos had put them together that year. Howard and Shelley were already well behind it. Howard, I, and Steve Weinberg wrote a paper saying how the coupling constants of the strong weakened electromagnetic interactions, which at normal low energy scales are very far apart, merge at higher energy scales. And that now is in the textbooks. So that's, everybody accepts that picture of how things work exactly in detail, how they come together at the end. Actually, since they don't merge to a very high scale, what happens between here and there can affect the details of the merging. And different things you add to the theory. If you take just the low energy theory and you take the precision we have now, they don't come together, but it doesn't take much additional. You can do it with supersymmetry, you can do it with extra Higgs to make them come together. And the other paper I mentioned with Enrico Poggio and Steve Weinberg, we called it smearing. How do you look at a theory where you calculate quarks but you observe hadrons? How do you predict the hadron behavior from the quark behavior? And you have to somehow average over energies a little bit. And then you can go from one theory to the other. And we showed that formally for E plus, E minus to hadron calculations. But it's then beyond that, the industry of calculating jet physics, it's called, where when that one quark gets knocked out of the proton, it gives you a jet of hadrons eventually. And those calculations are now a very high-level theoretical industry to be able to match what we can measure with what we can calculate. And that's an important piece. Getting from the fundamental underlying theory doesn't actually talk about the world as we observe it. And the theory that takes us from the fundamental underlying theory to the world as we observe it is also an important part of being able to test the fundamental underlying theory. And this is one of the beginning pieces of that. As I said, end of 1974, discovery of particles containing charm and anti-charm quarks. Gary was there. And it was a very exciting event for me. It was the most exciting event in my career. Coming into Harvard that morning after the talks at Stanford had revealed the results from 2 different experiments that said there are particles that contain charm and anti-charm particles. To us, that's what they said. We immediately said, that's the interpretation. It's exactly what Tom and David Politzer were talking about in their paper on charmonium. We're seeing what was predicted. There were, however, lots of other interpretations because there were lots of details that didn't quite fit until we knew other things in addition, and we went to higher energies and saw the pieces that made it work. But this began to solidify belief in the standard model across the particle physics community. So I think I date the end of the emergence period with the discovery of charm. A personal aside. In 1970 and 71, Dan, we were postdocs at Daisy. That's a whole nother story. And Dan got a job as an assistant professor at Tufts. And I said, if there's any city in the country where there ought to be 2 jobs, it's Boston. So yeah, take the job and I'll find myself a postdoc. And I didn't. I had a year without a job. I looked around and I said, what do I do now? First of all, I got pregnant. Secondly, I took education courses at Tufts and did student teaching in a high school, thinking maybe I'd be a high school physics teacher. And then I met Joel Premack, who was then a junior fellow, in somewhere around Harvard Square, and he invited me to come talk, and I came and sat in an office here without a job and started doing particle physics again. And so that was an important transition for me personally. In March 1971, our first child was born, and Sydney offered me a postdoc here. Sitting in my office, I said, this is wonderful. Now I have a career in physics again. And so that was the beginning of my period. So when you say I came in 1971, actually I came at the end of 1970. From 71 to 76, I went from being a postdoc. I also had another child. There's a funny story there. In March of 1973, the department was planning course assignments. And I took the chair aside and told him quietly, I'm planning to have another child. I don't know exactly when, because I'm not yet pregnant, but you should give me a course for the 2nd semester next year that will be easy to replace me. Within days, everybody in the department knew I was planning to have another child. And if I wore a loose dress, they all were looking at me and asking questions. But okay, he actually did arrive in the January of 1974. Harvard messed me up by changing the calendar that winter because of some energy crisis. And he was born the day I was supposed to be supervising the final exam for the course I was teaching with Jerry Holton. So I didn't get to be at the final exam, but he was here when I was grading papers 3 days later. So he definitely was part of this story. So here's a picture of me with my 2 children. I think this was spring 1975 in Somerville. This one comes from here. Somebody decided there's so few women in physics, we have to do something about it. We'll write a brochure for women in physics. It basically says, you can be a physicist and be married and have children too. With a lot of words. But it also quotes me, so I quote myself from that time. to say I was just enthusiastic then, as I am now, about what was happening in that time. And one of my friends called it, you have 3 infinite time sinks. One is research in physics, one is having children, and the third is owning an old house in Somerville. So that was that period in my life. But this, those of you who look closely can recognize an office in Jefferson with the window out across the parking lot and the trees across the way. A word about the atmosphere. I showed this slide at Howard's celebration. The atmosphere was quite thick because Sidney never was seen without a cigarette in his hand. Howard smoked a pipe. Shelley and Alvaro liked cigars after lunch. And we were writing a paper together, Howard, Shelley, Alvaro, and I. In Howard's little office, I would sit on the window ledge with the window open so I could breathe because I was pregnant. And then it got to be December. They made me close the window because it was getting too cold. And I stopped sitting in the office with them. But on the other hand, it was exciting, it was fun, and we were all working together, and I felt totally accepted as a member of the group. I think maybe I began to condition Howard's attitude to women in physics. He, from then on, had lots of women as students and has always been really supportive. But I like to think I had some influence on that, but maybe not. Maybe he would have been that way even without me. And both of my kids spent the first 6 months of their life in this building until they started crawling around and I couldn't leave them in a basket anymore. And nobody seemed to mind that. I sat in the back of seminars and nursed them to keep them quiet. I only once had to walk out of a seminar. It was a seminar, an informal seminar in the room. I don't know if it's still a seminar room around the corner there. And I came in a little late, so I was sitting on the floor with the kid on my lap, and it was a little uncomfortable. I walked out of the room. Afterwards, somebody said to me, "Did you pinch that baby?" Because it was such a bad seminar, they wanted to walk out too. But, okay, enough fun. Go on with the consolidation of the Standard Model. From 74 to the present, it's just been one test after another, and the level of precision at which calculations can go continually gets better. The level of precision at which the experiments work keeps getting better. And the theory is frustratingly good. It becomes broadly accepted because it's so good. There's increasing precision, and there's lots of work to say, okay, now we know this, what more do we need to know? Only one major correction, which is to add masses for the neutrinos. You don't have to read the list, it's just to say there's a long list of things that fit the theory by 76. And it keeps going year after year. I just give you a couple of examples. This is one parameter. It's actually the strong coupling constant at a particular scale, the mass of the Z. And each one of those points with error bars is a different measurement, entirely different measurement of a different thing, of the same parameter as extracted from our calculations. If the theory has this coupling, then we see that. And the black points are calculated at 3 loop, next to leading order calculations. The open loops are second leading and second leading order calculations. And it all fits together. I don't know of any other theory where there is so much data that fits it precisely. Right? And this is one particular piece of that data, just to show you. Another piece, this has to do with the piece of the theory that there's the Kobayashi-Moskawa theory of the breaking of CP violation. There's a little black triangle in the middle of that thing. That's the theory. And it has, as any triangle does, only 3 parameters. Every different color is a different measurement. and the band allowed by the measurement. And you see that there's overlapping, so the little triangle fits the measurement, and the measurements as we go across the years get better and better. And the theory says that the measurements we have that tell us about CP violation fit the theory beautifully, and it continues to this day. So it's just having a theory that can do this kind of precision work is a wonderful advance over the way particle physics was when I was a graduate student. And we can rightfully be happy that we got there. Right? The one revision is neutrino masses. It really doesn't affect much of the rest of the theory, but you have to do something more to extend it to add the masses in. And that's an interesting piece of the story. We know the theory isn't everything. It doesn't explain certain things that we do know. In fact, the CP violation piece doesn't help us explain how the universe is full of matter and doesn't have very much antimatter. But knowing that it's not complete means we want to go beyond it. But unfortunately, because it's so good at fitting the data, we have very little experimental clue as to which way we could possibly go beyond it is the right way. And that's why I say it's frustratingly successful. Well, it's getting close to the time I should be stopping. But if you want two more short Weinberg anecdotes, I think we have time for that, and then questions, right? All right, so the first one, I was riding with Weinberg in the car, and the radio was on, and they were announcing Saul Bellow's Nobel Prize in Literature. And Weinberg says, you know, getting a Nobel Prize in Literature can't be such a big thing because everyone knows who you are already. And I thought that was, it told me he was thinking about getting a Nobel Prize, and he was thinking about how getting a Nobel Prize would change his life. He thought Saul Bellow was already sufficiently famous, so it doesn't matter. But I don't think it was probably true for Saul Bellow. The other one has to do with Schwinger. So Julian Schwinger, when he left to go to UCLA, for some reason, probably absent-mindedness, left a pair of shoes in his office. Dress shoes that he obviously left there for when he wanted to go to some fancy event. And we used to tease Steve as to whether he could fit into Julian's shoes, which he surely did and more. But then Schwinger came back to visit, give a series of Loeb lectures, and have the PhD oral for his last student. And the oral committee was me, Schwinger, and Steve Weinberg. And the student was doing something called source theory, which was Julian's way of reformulating quantum electrodynamics. And Steve didn't particularly like source theory, so the student started to speak, and Steve started in to ask him questions about why source theory, with Julian, the founder of source theory, sitting there. So Julian, of course, jumped in to defend his student, so the student didn't have to explain the theory that he was working in, but could explain his own work. And it turned into an argument between Steve and Julian about what is a good theory. And I wished I had a tape recorder, because having two Nobel Prize level physicists discussing the merits of different types of theories. And really what it was Julian was saying the best theory is one which can absorb all new information. He was really talking about a type of theory, a class of theories. Whereas Steve was saying, no, you have to have an explicit realization so you can test it and rule it out if it's wrong. And so those 2 points of view, I think they're both right, but they have to be seen as, what do we mean when we say theory? Do we mean a theory, or do we mean a type of theory? And of course we mean both. So that's the end of my story for today, and I managed to finish exactly at 7:30. And I hope some of you have some questions. Is this? Howard has a correction.
No, I have something that I'm fascinated by. My memory was that one of the things that really got us started in the right direction was a talk by Ben Lee, the great Korean physicist. And it sounds from what you said that you and Joel and Tom were already calculating.
We were actually when Ben came, yes.
I see.
Ben was doing, as I say, Ben very quickly had that full proof of renormalization. But the reason he quotes us, and he quotes us as Appelquist and Quinn, not Appelquist, Premack, and Quinn, because he didn't even have the preprint of that paper. But he had talked to me and Tom while he was here, and he says that calculation, because they're, to be technical, their proof is all in R gauge, and our calculation was in U gauge, and his third paper is about the equivalence between the gauges, but he quotes our paper as being part of the indication. So he came to talk about that renormalization paper, which is very roughly the same time, but we were already working on it.
Okay, interesting. I actually have one more question, which you should feel free not to answer if it's privileged information. Is it really true that Dan didn't tell you anything about what was going on in Ting's group about the J-psi?
In Ting's group about the J-psi, I already had left. Okay, we were in Stanford, but we were here by then.
Right.
Dan was no longer in the Ting group. And when you leave the Ting group, you don't talk to the Ting group.
Got it. Okay, that explains that mystery.
He knew how to look at pairs of particles. I knew that much, but I didn't know he'd seen anything.
Got it.
No, Dan didn't know. The real question is, so for those of you who are not in this history, there were two experiments I said gave talks the same day at Stanford. One of them was Ting's experiment, which was at Brookhaven, and they had that result months before. Ting will never believe that somebody didn't tell the people at Stanford about that result. And then they went back and looked for it at Stanford. But in fact, the people, if you look at the history of the publications, if you look at the first publication from E plus E minus to hadrons, and Bert Richter came here while Tom and David were talking about charmonium. He didn't come to their charmonium talk, but he was talking about rising total cross sections and how no theorist could understand the data. But in fact, when they plotted, if you go back and look at the paper, you'll see a 2 or 3 standard deviation high point, which is the J-psi in their original publication. And they amplified the errors because those errors that they showed were the total normalization uncertainty, not the point-to-point errors. And so if they'd plotted the points with only the point-to-point errors on them, you would have seen much more than 2.5 sigma in that original publication. And it was that point that they went back to check, that the people at SLAC then found, because they went back and they didn't tune to exactly the same energy, so they got more to the place where the narrow peak is, and instead of hitting the shoulder of the narrow peak, they hit the narrow peak, and saw the resonance there. So I think it's really true that it was a totally independent discovery. I'm really convinced of that. Gary, you can have an opinion on this too, but
I always assumed that it was possible because Richter was out of town here telling us about his theory of
well, maybe that they went back, that they could go back to Richter was pushing to get to the highest energy possible, and to do this they had to go back to a lower energy to check that point. And they somehow got permission to do that. I don't know the internal dynamics. Gary might tell me more.
Well, yeah, Roy Schwitters actually gets credit
Roy did it, yes,
for doing this, because he was studying the total cross-section runs and found this anomaly. And I remember discussing this in the SLAC cafeteria about what are all the possibilities of this.
What is causing this
being real
anomaly?
or not.
Yes.
And one of them, for instance, was with James Patterson, who was the key accelerator physicist. And so Roy posed the question to him, was it possible that the luminosity somehow fluctuated up enough to create this peak? And
he said no.
He said absolutely not. It was just not possible. So there was a real mystery there. And the as you mentioned, the irony of this is that while we were doing this experiment, Bert was off. Was it here?
He was here giving lab lectures
about the total cross-section rising.
Right.
And the theory of that.
He was saying theory is completely incapable of explaining this data. The other piece of that history is in 1972, BJ and I wrote a memo, which we sent only to the leaders of the experiments, saying, look, in this, we sent it to Bert Richter and Jerry O'Neill and a couple of other people, saying, you should search for narrow peaks, because either charmonium or additional heavy leptons will give you these kinds of narrow, if you're trying to explain away the neutral currents, you're going to have to add something to the theory, and whatever you add to the theory to explain away the changing neutral currents are going to give you narrow peaks. So you should be, and they came back and said, we can't. And it was true. It would have taken, to search point by point for such a narrow peak would have taken forever, right? So they said no, but it was really that Bert really was interested in, is the total cross-section rising at high energies? And he was the leader of the experiment, so he was pushing to high energy. So they ignored our memo. But I think Roy remembered it, because Roy told me about it.
Hey, that was very nice, thank you. I just want to hear a little bit, I mean, you were very lucky in many ways. You'd be here during the early 70s, but you were also at SLAC during 68 and when they found.
Yes.
And you were working with BJ who.
So I was very lucky there too.
Yeah, you're just like an insanely lucky person. So I just want to hear a little bit about what it was like to be at SLAC with BJ as a who also should have got the Nobel Prize.
Right.
With Saul Bellow. And then just what it was like that in your graduate career there, because it seems very exciting.
Well, I think, almost any graduate student is overwhelmed by new information, right? So I was being overwhelmed by new information at a time when the field was also, and I don't think I was sorting out what was new to the field and what was new to me. But I remember distinctly BJ showing me data from the slapdick inelastic scattering experiments and saying, look, this tells us that there's particles, he called them partons because he was talking to Feynman too. He said they're clearly we're seeing the partons, and partons today, the word parton means either quark or gluon, but back then it meant any substructure particles within the proton. He said we're seeing the evidence for a particle being hit and knocked out of the proton, and this is the way you see it, and here's the data. Before anybody in the world was seeing that data, I saw it with BJ. So at Stanford, I was already moving towards the standard model. Then I went away and did a postdoc in Germany where nobody was interested in that stuff. And then I came back here and got back into it. So yes, the pieces built together.
You still want to ask something?
I'll ask it then.
It's just is it working? Yeah. It's just a comment on Julian Schwinger's shoes, actually. I happened to, in 1976, when I first came here, Weinberg was on sabbatical, and I was privileged to sit in his beautiful office, and there was a closet in it which had Julian's shoes. And they were, I think, size 14 or 15 or something, so Weinberg could not
That's true. That was part of the joke, of course. The shoes were much too big for Steve.
His shoes or not, but they were huge. And somehow, over the summer, at some point, I think, over the summer, they disappeared from the closet. And Steve accused me of stealing them, and he never forgave me or believed me. I said, I don't know what happened to them.
Yeah, I'll tell you, this is just a comment. I'll tell you how far we've advanced since the days when you were raising your children in your office. We now have a private nursing room here at Harvard.
Yeah, that certainly didn't exist. And anyway, I wasn't shy. As I said, I sat in the back of the room and I nursed them. Most of the people in the room, maybe they heard the baby, but they didn't pay much attention. But sometimes I saw a seminar speaker give a real double take when they realized what I was doing. Because often I was the only woman in the room at that moment, too. And I didn't really think I was being radical. I was just doing what I needed to do to make my life work. Yeah, the young people should ask some questions.
Go
ahead. Thank you for sharing this fascinating story. As a graduate student in particle physics in the department, I think I can speak for many other of my colleagues. Like, it's very fascinating to hear this. What do you so you said, like, now the standard model is in this consolidated phase. In what phase are we talking about the next theory?
I think particle physics needs new data to know where to go next. But it's really very hard because it's very expensive. And figuring out which direction to move, I kind of like the people who are testing particle physics theory with low energy experiments. Partly because the axion searches are in that field, but also partly because I think there's some really interesting ideas there for how you test a theory with precision rather than with energy. And that's a direction. From a theoretical point of view, I have no good advice to you. I haven't been doing particle physics theory since 2010. I'm not really current with what's the right place to be right now. But it's a difficult time again in particle physics to know which way to go, I think. But maybe there's hope in the fact that, there are cycles. There are stages of confusion and then stages of emergence and then stages of consolidation. We've had a very long consolidation. Maybe something will break things loose, or maybe you'll find different applications of the things we know already.
So, is this working? Okay. So, as a new graduate student and not having much research experience, what advice can you offer for when to stop pursuing a new theory versus when to keep on going, even if people are telling you, "Oh, stop! There's nothing to it."
Well, I think exactly. What to do and what not to do is probably the hardest question in doing research, right? Which problem is the problem that's ripe and ready for answering with what you know now and will move you forward, and and even when you're doing one of those, you're going to have times of frustration where you're working for a long time without feeling you're getting anywhere. So figuring out if you're not getting anywhere because it's just the wrong problem for you at this time, or if you're not getting anywhere just because you haven't quite found the right approach, but you're actually making more progress than you think, it's very hard to tell. So I don't have any good advice as to how to make those choices, but I think those are very serious choices you have to make a career in research.
Hello. I will ask a very selfish question. You are a phenomenal scientist and someone who truly grasps what education means. And I am just super curious to know, how did you end up taking that pathway? And in general terms, how are theories and ideas different or similar between physics and science and engineering education?
See, Grace is an engineering educator at Tufts now. She was a graduate student at Stanford, and we talked a lot about science education together. I think it depends what we're talking about. I think in education, there's a building and consolidation, but it's not as easy to build one theory on the other as it is when the theory is mathematical and you can really see how the pieces work together. So theory is quite different in educational theory than it is in physics theory, partly because it's not as cumulative. And I don't know how you make social science theory cumulative in the same way physical science theory is cumulative. So that's really the answer to your question. As far as, I'm not really sure what the first question was, but how I got to be who I am has many pieces, of course, as it does for any of us. I think one of the things that made it possible for me to have the career I had is that I grew up in a family with 3 brothers and a father who liked to foment argumentation around any topic. Right? It was his favorite thing to do, to pose a question that would get us all arguing. And he expected me to give as well as I got. So I learned to argue with the boys before I ever started learning physics. And that, I think, was important, allowing me to do what I did at the time I did it. The other piece is I had a very good secondary math teacher. Physics teacher, not so good. But my math teacher said to me in high school one day, she said, "Helen, you could be a mathematician because you are so lazy. You never do a problem the hard way. You always have to find a clever way." She was actually frustrated with me because she saw me studying for a 3rd time on a problem that I didn't like what I was doing. But I heard the praise in that remark as well as the criticism. And somewhere it led me to feel I could keep going occasionally when things were frustrating. So little pieces that you say to people sometimes can have big effects. The other reason, why am I a physicist? Well, if my family hadn't migrated from Australia to the US when they did, I would be a meteorologist and probably a climate scientist today. Because I was at Melbourne University with a cadetship from the Australian Weather Bureau that said I had to work for the Weather Bureau for 5 years after I graduated with my degree. And one of my friends from that time is, in fact, one of Australia's top climate scientists. So I know that's the direction I would have taken. But this fellowship, how did they say I had to work for 5 years? Well, if I didn't, I had to pay them back. The money, and they'd pay me a salary while I was a student and pay my expenses as a student at Melbourne University, which wasn't very expensive, but still it made a difference to us. And the other part of it was I was not allowed to marry for 3 years after I got my degree, because at that time the Australian government didn't hire married women in permanent jobs, and anything more than 2 years was considered a permanent job. So part of the contract I signed was I would not marry for 3 years after my degree. My father said, "Sign it anyway, I can pay the bond if you have to." Then when my family moved, I went to the Weather Bureau and told them my family was migrating. I was 17, right? So they said, "Okay, go with your family. I think that circumstance is beyond your control." And I didn't have to pay anything back. So I arrived at Stanford with 3 years of credit, one for the last year of high school in Australia. And I needed to find a major I could complete within a year. And I had this general science major at Melbourne, which had some physics and some math and some chemistry. And so I went around the departments. And I ended up in the physics department. And I became a physics major because the professor I was sent to in the physics department was Jerry Pine, and he had a very flexible attitude about requirements. And he told me, well, if you think you've had it, I'll sign you've had it. And if you think you need to take it, take it. And I had a quarter when I just arrived, which was January 1962, where I audited courses and decided, okay, I could get myself up to speed with the junior level physics courses and finish the year taking that last quarter and the next year and graduate in 4 quarters. And I knew my parents couldn't afford much more than that, so that's what I did. And that's why I was a physics major. And by the end of that time, things were getting exciting at SLAC, and there were a lot of people excited about particle physics, and the faculty encouraged me to apply to graduate school. I'll tell one more anecdote. And my undergraduate, I told Melissa this earlier today, my undergraduate advisor said to me, you know, graduate schools are often reluctant to accept women because they get married and one thing or another, they don't finish. But we don't need to worry about that with you. Did he hear what he just said? It was actually what I thought. But you know, I think you could interpret multiple ways. But, I wrote to Princeton and said, would they accept a woman in their graduate school? They said, wrote me back a letter addressed to Mr. Helen Arnold. And it said, we do not normally accept women. So I decided I was not abnormal and I wouldn't apply to Princeton. I applied to Harvard. They didn't accept me. Only Stanford accepted me, so I stayed at Stanford because they knew me, right? I had to be where people knew me before I could make this career. And so I stayed at Stanford for my graduate degree, which was fine because I had a boyfriend and who became my husband. And that was the pattern of my life was I had to be somewhere to get the job, to get the admission. So I think that was part of the times.
Well, on this note, I'd like to thank Professor Quinn again for a wonderful historical lead lecture. Thank you.
Thank you.